So just to quickly, where do we leave off, right? Like, we were talking about really, you don't want to compare instances of runs. You want to compare distributions, okay? So pick your favorite how to compare distribution strategy. But it's not just about comparing distributions. Just because two distributions have a very low p-value comparing them, meaning that the odds of them coming from the same random variable is very low, that doesn't mean that their difference is like meaningful though, okay? Like, yes, this data definitely came from two different observable things, but like, it's great that the distributions came from different things, but like how much of a difference was there though, right? So that's where you're talking about things like effect size to measure like, okay, was it better? And you got a couple of ways to do it, like standard difference or something, right? Cohen's D between, there's a couple of strategies. If you load up SciPy, did you do your analysis with Python at least? You're getting there. Okay. I recommend not using C++ for like analyzing your code. That would just be horrendous. Load up SciPy, scipy.stats, pick whatever you want, right? Open up the documentation, Control F, effect size, whatever one you want, right? As long as, and look, raise your hand in here if you're a statistician. Okay, so look, do your best. Obviously, pick the ones that make the most sense, but I'm not going to be, like, the marker and I aren't going to be going there being like, oh, in this particular case, you shouldn't have used that particular test because this is what you mean and you made the wrong look, just have sanity, do your best, figure out the best ones to use, right? But like, we're not going to go crazy, okay? All right, perform comparisons, yeah. Now, everyone asks like, okay, if I'm comparing distributions, how many observations do I make? For whatever reason, it seems normal where people do 30 runs. 30 is like the minimum. Do 30 runs, you've got your distribution. I'm not 100% sure where 30 came from.
I think that's for the CLT. Like in terms of normal distributions, like 30 samples is kind of like the minimum.
Is that, yeah? Yeah, but that doesn't mean it's a good number.
Yeah, but that's what they use.
Well, whatever. Anyways, I always would do like 100. Just because it gave you a little more of a clearer distribution, especially when you're dealing with stuff that can be quite stochastic, because it might look pretty chaotic until you get there. Now, there is a funny side effect, though. Like, the bigger you make n, the more likely you are able to find a difference between distributions because you add like more resolution to the distributions. So if you wanted to find like a significant difference, you can cheese it by being like, I made n 10 billion, and yes, they're two disparate, but that's kind of, no good. Just pick a reasonable one. I'd say 100 runs. That's time dependent, right? Like if you're running it and it's due tomorrow night and each run takes 2 hours and you have to do 200 hours, okay, it's not going to work, right? So do what you can do, right? So compare each one based on the above, tabulate simple summaries. Here's my advice to you. One, okay, like get your results. Based on what you get some tabular simple summary statistics, right? I'm pretty sure there's like a scipy.stats.summarize or something. And it'll just split out like everything, like basic statistics, like IQR and confidence intervals and stuff, right? So you can get some of that. That's always nice. Plot the distributions, like in the above figure. You're going to want to make sure it's plotted with the same like X scale. Sometimes, like depending on how you do it, the bins might be wildly different, and then like the bin sizes. Like this one, it's not like it's n queens, right? But let's say you're doing, so it's a small number, clearly very integer-y. Each bar is one integer, right? But if you're doing something like TSP, where maybe it's like you've got sizes that are huge. Like, has anyone done that yet? Plotted their TSP results in a distribution? Yeah. Yeah. So when doing it, one distribution, when you do it, like automatically it'll pick like a bin size for that distribution, and it'll be like, a bin size is like the bar.
The default is 10 bins.
The default is 10 bins, which is great, but the problem is like how many X values are in there. So what I mean is, let's say this is a scale from like 0 to 1,000,000, right? I can't have 1,000,000 ticks here. So you're going to have blocks of like thousands, right? Where it's like, these are how many between like 4 and 6,000, for example, right? But the second distribution, it'll try to do 10 bins, and maybe its bin sizes are different. So make sure you have a standard bin size between each one. It's really easy to do in Python. When you do hist, when you do like plt.hist, one of the keyword arguments is like bins, and you can give it like a list where it'll do like the bin sizes. So you can set it pretty easily. Yeah?
Also, I think I did it with if you have your I guess your numbers, just your list of valid results in as columns of a pandas data frame.
Oh yeah.
You can do df.hist.
Nice.
And then that gives you all the gives you all of them in one.
Perfect.
With the same sort of.
Perfect. Yeah. I for whatever reason I never like used pandas a lot, but I know how immensely powerful it is. So if you like it, by all means, it might make this assignment way easier if you use pandas. Pandas is a non-standard library that's it's like kind of like the standard library ++ for Python, I'd say, where it's like it's non-standard, but everyone's using it. But anyways, that was the warning for that. Whatever. Okay, perform some tests to compare the distributions. Do some effect size. What conclusions can you make from these results, right? If your conclusions at the end are like, I invented 17 new mutations that I all thought was great, and they all sucked. That's fine. It doesn't matter. Never feel like you need to falsify. It doesn't matter. Your conclusions could be like, it made literally no difference, or somehow it made everything 10 times worse. That's fine. It's interesting. That's the point, right? Good results are almost like boring because you're left going like, yeah, okay, sure it worked so well, right? Right? Like, what did you do wrong, right? Anyways, any questions about general ideas for your comparisons, right? Yeah.
I think a comment on what you just said, the good results part. So I tried implementing the HBRM one, and then it converged so quickly. I was like, is there any way I can make this like last so long before it converged?
Yeah.
So it was just like boom,
Mm-hmm.
point. And then the first ones I was trying was like about 5,000 generations, and it's still like at the very top. It's not really convergent. So I was like, which one do I use? I guess in a way, I don't know, but if it's really looking at if you plot and it's really like convergent over time, I think that looks beautiful.
It does. There is a nice beauty there.
That's the one I'm looking for. I don't want the
Yeah.
one.
But then it's like, well, if it goes fast and it's better, and then you're like, man, right? Like, crap. Yeah. Yeah, right? And like, remember, like, if you go find something that's like designed for TSP, it's probably going to do pretty well, right? And that's okay. But at the end of the day, what's being looked for is what are the conclusions you can make. Like, what is the discussion? Are you capable of having a compelling discussion about what you got, right? If your discussion is like, look, we did all this comparison, and honestly, it made no difference. I guess it didn't matter, blah, 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 blah. Fantastic. That's kind of what we're going for. All right. Okay, so now what we're going to do is we're going to be going through a series of topics that kind of get into some of the individual things within like those modular things, like what are some genetic operators, selection and population management. I guess we already did representation, right? So, okay, I guess it's only the two topics. And then we're going to get into genetic programming a bit. We'll talk a little bit about how to tune hyperparameters. This is like later. I'm just giving you like a little bit of like a roadmap here. What it means to compare distributions. So we did just talk a little bit about like p-values, but I'm going to give you a little bit of like intuition as to like what does it really mean when you're doing it, okay? When you're comparing like what do you mean? How do we know? How can we magically know like they're different or the same, right? So I kind of explained that a bit to give you some idea. I find, at least with my experience, both as a student and as like a professor, most students like raise your hand if You've used like a t-test before because you had to, right? Yeah. Raise your hand if you're like, I know what it really means. Yeah. See? And that's fine because that's honestly how we've been trained. It's how I was trained, right? But at the end of the day, there's actually a very intuitive explanation. And we will get to that, but a little bit later, okay? So for now, just keep doing what you're doing and be like, it's a p-value. It's less than 0.05. That's good, right? Right? Yeah. Okay. Then we're going to get a little bit into swarm intelligence. Then, at this stage, we're probably going to be around the time where lectures are going to take place, right? So I have to like work back from like, okay, end of the semester, okay, if there's like one presentation a day, there's 11, that's like 3 weeks and a little bit. Okay, perfect, right? Like we'll do that. So that's why like the content kind of stops because there's a point where you're doing things and you're trying things and then you're giving the lectures that we all get to experience and gain from, right? I could sit here and teach you things like evolutionary strategies, differential evolution. I could do that, right? But at the end of the day, once you know what like a GA is, and we'll spend time talking about like particle swarm optimization, which is very different but the same, genetic programming. Once you know that, you can go and learn differential evolution like that, right? Where I think you're going to gain the most is people presenting what they did in like a research setting. Like, here's what I tried, and you get a sense of like how they're used, what worked, what didn't work. That's where you're really going to gain the most, I think. So that's why it kind of cuts off there. If you're wondering like, isn't there more? Yeah, a lot more. But I don't think you're going to gain as much as you would from like these lectures. All right. Genetic operators. Okay, so look, you're already familiar with some. Who tried to like invent their own genetic operator for the assignment for fun? One person? Only one? Okay, well that's fine, right? So you can invent your own. Really, like I was saying, do what you want to do. Am I recording? Yes. Do what you want to do. But I'm going to give you some of like the standard genetic operators that you see for a variety of different representations. They are well, I don't know what else to try right now. I guess you could start here, right? But everyone kind of knows that they're just like a starting point, right? Maybe, and a lot of times they do work well, so maybe you don't really need to go digging any deeper, but they're kind of like your standard quintessential run-of-the-mill. These are your basic tools in your tool belt. These operators, there is going to be a focus on genetic algorithms. There would be like genetic operators that maybe are specifically designed for other types of evolutionary algorithms. But for the most part, because the GA is like your basic one, I think this gives us an opportunity to talk about genetic operators in a more general way and how like they work on most of these algorithms. Now, look, binary representation, genetic operators. This is that representation where, although you could encode anything with the binary representation, anything you're like encoding in the computer, you're not really seeing this one very often anymore to like as a general purpose representation. You're going to see this representation for maybe like Boolean things, right? Where maybe you do need a string of Booleans or something. Okay, fine. Something like one-point crossover would work just fine here. The idea is randomly select an index, exchange the elements between the chromosomes after that index. So here's a picture, right? Hopefully this is rather clear, right? You got the two parents. Imagine the extreme case of all zeros, all ones. You pick a point, you flip them between the point, right? That's it. If you're asking the question, well, should it be before or after? Like that's not an index. That's 0, 1, 2, 3, 4, 5. That's between 4 and 5. If I pick 4, should it be? You're missing the point. The implementation details, right? It's like you pick an index, you swap, right? Yeah. Usually I would say like if you pick 0, you want everything from 0 to the end, right? So usually whichever index you pick, it's that one inclusive. But it doesn't really matter. The point is it's one-point crossover. This crossover is not particularly destructive. Now, I've talked about like destructive operations before, and this is kind of like a hard to like put your finger on concept, but hopefully you get the idea. It's like the amount of information within the chromosome that gets like changed, that gets like destroyed, is very minimal here, okay? Now, you could say, well, no, it's a lot, right? It's like more than half of the chromosome. Yeah, but often a lot of like what these mean is like this batch of information wasn't like catastrophically destroyed. It was preserved, it just moved somewhere, okay? So that's kind of the idea. This isn't really that well of a defined term, but a lot of people will know what it means in the area of evolutionary computation. This crossover works really well when element adjacency in the chromosome is important, right? What I mean by that is, if the fact that this is before this, which is before that, and this comes after that, right? If like the order of the things has an important feature, like think TSP. Obviously, we're not using a binary representation for TSP, but like the order in which you visit the cities is kind of like the important thing there, right? Or maybe it's like instructions for that robot. Again, not a binary representation, but the idea where like the steps that the robot takes, like the order in which you perform the steps, is important, right? So there's only like one point where things get like mixed up. Then we have endpoint crossover, because we could be like, well, there's 2-point crossover, 3-point, you can have endpoint crossover. It's the same idea, but it's like just generalized. Randomly select n indices. Exchange the elements between every pair. If it's an odd number, you exchange between the last pair and the end. Fine, it doesn't matter, right? So here it would look like this, right? So here's 3-point crossover. So when comparing this to 1 point, same idea, right? Straightforward, nothing crazy, and it preserves chunks still, but I think you kind of know what I mean where I say like, but this is a little bit more destructive. You see what I mean? Yeah, and like the benefit of this is, like if you think of endpoint crossover, that n gives you a dial of, well, do I want to make it more destructive? Should this change over the course of evolution? Or should it be fixed, right? Like it gives you a little bit more flexibility. Though, like everything in this thing, in this course, a lot of people will complain, like one of the complaints of evolutionary algorithms is the number of like tunable parameters is so freaking high that like, oh, you're adding another one? Great, right? So, to each their own. Uniform crossover. Select some random number of indices at random. Exchange the elements at those indices. Often you want to implement this by giving each index a 50-50 chance to be selected, but that doesn't really matter. The crossover is pretty destructive, and it's not particularly effective for chromosomes where adjacency really matters. So imagine I picked, like I would go through and be like, do I swap, do I swap, do I swap, do I swap? And you look at like each individual like pair index-wise. So here, this can then, like if you're thinking of endpoint crossover, like this can be quite destructive. And like, look, if adjacency really matters, this might really obliterate any of the adjacency value that you're getting pretty quickly. Mutations for binary operators. Bit flip, we saw that one already. If it's a 0, make it a 1. If it's a 1, make it a 0. The number of bits that get flipped is arbitrary. You could hard code it, be like, we're only ever going to flip 1. When you do mutation, 1 bit has a chance to flip. Or maybe you can make it random. Some number of bits get to flip. Or maybe like between 0 and 5. Whatever. Hopefully the point is, high level idea, do what you want. And yeah, randomly select one each time. Similar to uniform crossover, but instead of exchanging elements, it's just arbitrarily flipping, right? Because remember here, you might be like, okay, so it's basically bit flip. Well, no, it's not, because it is only because this is all zeros and this is all ones. This chromosome might have like a 0 here, and if we flip them, well, nothing actually changes. You see what I mean? Yeah. Yeah, so bit flip, great. Cool. Now, all right. And what else? Whatever other thing you want to do for a binary representation. You could do whatever you want. It really doesn't matter. It's such a simple representation that ultimately the amount of creativity you can have might feel a little bit limited. Fair enough. But whatever you want. So integer representations, not to be confused with permutation representations. Permutation representations might be of integer values, but I'm talking about like general integer representations where you could have any number of any value in any position. So this is, yeah, it works with integer values. Now, the crossovers for binary representation are also basically your default ones for integer 1. Endpoint crossover, uniform crossover, like here, like GA crossovers. Like there, look, what else we got, right? You can go find a whole bunch here. You could read the whole Wikipedia. Wow, this is bigger than it used to be. Good for them. They added to it. Nice. But if you read this, you're also going to get a sense of like, yeah, whatever you want, right? Don't let the flakiness of evolutionary computation concern you. That's the fun part, right? Of like, whatever. If it worked, it worked. All right, so mutation, well, like a bit flip mutation obviously isn't going to work very well because, well, if I've got a 7 and I pick it for mutation, what do I change it to? Well, usually what you do is you just randomly pull from the set of allowable integers and replace it, right? So pick an index and replace it with some random admissible value. When I say admissible value, I mean like, well, what integers could it be replaced with? Between 0 and 4 billion? Or should it be bounded? Should it be between like 0 and 9 or something, right? So you might have to constrain it, but the point is, this is kind of like a generalized version of bit flip, I guess. How many integers do you change? Up to you. Do you want to have it so only one goes or several go? It's entirely up to you. Okay, similar to bit flip, select an index, replace the value. Single point mutation can be generalized to endpoint mutation. Yeah, there you go, right? The mutation is helpful in situations where the value of the chromosome represents cardinal attribute. Yeah, okay, cool. There are other possible integer values do not necessarily matter. For example, the amount of values within a set. Where in the order? Yeah. So where the order of the possible integer values do not necessarily matter. Yeah, okay, yeah, cool. This mutation is also helpful in situations where each possible integer is equally likely to become within the chromosome. Yes, yes. Hear what I just said? I'll repeat it. In its default setting, let's say, let's say it's between a number between 0 and 9, okay? So I pick index x to be replaced. It's got some value in it, I don't care, all right? I'm going to go pick a new integer from the box of allowable integer values, right? Now, should I be equally likely to pick a 0 as I am to pick a 7, as I am to pick a 9? Or do I know something about my search space where like, you know, the distribution of what I expect to see in the result actually looks like something, where I should be more likely to have 7s than 4s or something. Do you see what I mean? Right? So maybe I should actually be a little bit more careful here. And that's entirely something you could work into there.
What's the selection type? You can adapt it. It's not permanent selection, but
Roulette?
you can adapt that to that because you scale them based on
Their fitness?
or fitness. And you can
Well,
use a separate thing just for that.
Here, all I mean is like instead of pulling from a uniform distribution of values, you can pull from like some other distribution. And you could like set that accordingly. Swap mutation, select 2 indices at random, swap the values at the selected indices. This one works really well for permutation as well. So raise your hand if you did this for the TSP one. No? What did you do?
It's kind of like that, but swapping a whole segment.
Oh, nice.
I don't know what's called segment reversal.
I think it's in here.
Fun.
We'll get there, yeah. In Python, it's nice and easy, right?
Exactly.
Yeah. Did you implement that one, or was it one I gave you?
It's one you gave me.
Oh, man.
It was
All right.
given in the list of possible mutations. I've read through them and I was like, that one's fun.
Yeah, cool, yeah. The mutation. That particular mutation is actually kind of nice for TSP, but that's a whole other thing. The mutation preserves the information within the chromosome. So no new information is added. So the value here is like, well, it's not that they need to be unique, where it could be value. Maybe that's why you're using this mutation, right? Like with TSP, swap mutation works fine. But the value here is it's not so much about preserving, but it's more about like, you're not adding new information, you're just kind of like moving it around a little bit, and maybe that's important to you. Creep mutation. This is kind of like single point mutation, and remember with single point mutation, I had the question of like, well, when I pull them out of the box, should every number be equally likely to come out of the box to replace it? Here, it's the idea of like, okay, I pick some index and it has a 7 in it. Maybe for whatever I'm doing, it makes sense that like a 7 could move to like an 8 or a 6, but not a 2, right? Right? Where would you use this? It entirely depends on what you're doing. Does it make sense for your needs? If it does, have at it. If it makes no sense, well, then ignore it. Maybe you don't know, give it a try. You don't know, who knows? When close to means depends on the context. Mutation is often used in a situation where the value within the chromosome represents ordinal attributes. Yes, where the order of the possible integer values matter. Okay, cool. And then we have our permutation representation. This is the big one, right? Because assignment 1 is all about this. Permutation consists of different orderings of some defined set of values. Now, multi-set, let's say, because maybe you can have the same value in the set twice, right? So for example, the representation used for n queens, a typical representation for TSP. Did anyone, I think I asked this a moment ago. For assignment 1, did anyone explore any different representation for TSP? No? No? It's a very direct one. There's nothing wrong with it, but you can do whatever you want. Like, I've seen like a shuffle chromosome where you have this like starting chromosome, and what you evolve is an order of how you shuffle the elements. So you take the standard permutation of like 0 through n, and what you're evolving are like, okay, swap 2 and 7, and then 2 and 4, and then 18 to 2. So it gives you like a step on how, so it requires a translation method where you take like your starting one and then you apply these to get one that you can evaluate. But you were evolving like a shuffling order, which was interesting, right? I think that's pretty cool, right? Yeah. And there's actually some value, but that's a whole other thing. No, well, no, it's not, because now the phenotype is the same, what it means, but the encoding is very different. What am I encoding, right? The shuffle order is different. So it's all like kind of like about intentionality, let's say. Now you could do it as an ordered list of n things, but it has like different meaning. Neither here nor there. Like we've already discussed, many of the previously discussed genetic operators become a problem for permutation representation because you destroy the permutation property. If we did, I think I showed an example of this, but just to make sure it's abundantly clear, if you have chromosomes like 1, 2, 3, 4, and a chromosome 4, 3, 2, 1, and you go like, oh, cross over here. Well, you end up with 1, 2, 2, 1, and 4, 3, 3, 4. Obviously, you've got a problem. They are no longer permutations. So, no good. Similarly with like 1-point mutation or single-point mutation, if you replace the value at the index that you select with any value other than itself, it ain't gonna work, thereby eliminating its efficacy altogether. Okay. Order crossover is a popular one for permutation representations. Was this the one that we covered already, or did we do another one? There's order, partially mapped. Was it partially mapped? Cycle, okay. Okay, look, this is my least favorite part of the semester, is talking about these crossovers because they're like, oh my gosh. Okay, so bear with me. If you want to use these, I recommend look them up again later because, you know, I'm going to do my best.
I used it.
Pardon?
I used the order crossover.
You used order crossover? That one's kind of like straightforward. That one's actually not too bad if I remember correctly. Okay. Order crossover. I think we explained this. Yeah, we explained this one already, right? You pick a segment, that's good. We like that, especially for something like TSP. This one makes sense, okay? That's not to say the other ones can't be good, but there's motivation. So you pick a contiguous thing, and you would do this twice, right? You would do this where you take this one, and then you would do another one where you start with this one, right? Of course, I'm only showing one of the children. So you take this one, and then you go through and go like, okay, from the other one, add a 1. There's a 4, skip it. Not 9, okay? 3, 7, there's already a 7, skip it. 8, 2, there's already a 6, there's already a 5, but we're done anyways. That's the idea, where you get the information from the one and the other. Some of it is nicely preserved, this contiguous chunk, where the other part is not as nicely preserved in terms of its ordering. It kind of is, because like if you fit, like in this example, it's not bad, but like imagine I take a 9, not a 3, but a 7, 8, and 2 or something, right? You're like, well, it's still in its order, but like some gaps kind of got introduced. So this one's like not too destructive. So it's nice in that sense. Okay, partially, I think specifically, when I said this is my least favorite part, I specifically mean this one, partially mapped. It's funny too, because back when I was in grad school and I was taking a class on evolutionary computation, unfortunately we're out of time for today, but so I can like prep it for Wednesday or something. But back in grad school, when I gave a lecture on partially mapped crossover, and I gave a lecture on it, right? So this has cursed me for a very long time already. And every time I look at it, I have to like re-remember how it works. And I convince myself, but through the process of convincing myself, I'll then look at the class and everyone's just like terrified. So anyways, until next time, see you later.